Testing, 1, 2, 3. Testing, 1, 2, 3.
All righty. Good morning. Can you all hear me? Yeah, it seemed a little low. So let me see. Is this any better? Slightly. Sometimes you just have to like put it right in front of you. Is this any better? Yeah. Okay, I see non-commitment here. All right. 10:20. So maybe if I just, have a certain directional tilt for the entirety of the lecture, this might work. Let me switch sides. Is this any better? Yes, because I'm facing this way. Okay, fabulous. All right, let's get this show on the road. It is 10:20. So let me switch over to input to see some announcements. It'd be nice if there wasn't a black screen. Okay, let me switch over to the announcements page. I just want to take care of some administrative housekeeping things before we start. Just a reminder, as you probably have already surmised or have seen the Carmen discussion section, that recitations do not start this week. So I guess this really only helps the Thursday folks. But in addition to recitation hours, recitation section starting next week, office hours will be starting next week as well. And if you've already checked out our Carmen page, you would have seen some of the modules on there. So I just wanted to take up to a minute to just go over with you so that if you don't see something, there's a problem, okay? So we'll go over the Carmen right after this. Homework 1 is already open. You should have access to that. If you don't, please let me know. It is due 2 Fridays from now, the 17th at 5 p.m., okay? And a student pointed out to me that on the registrar section 9724, which is Tuesdays at 9, the location has been changed. It was previously assigned to Denny Hall. Now it's Caldwell 133. So if that pertains to you, please make a note of that. I've updated the syllabus. I posted a preliminary syllabus back in November, so I've changed that now since we've started classes and some things have changed, and this is one of them, okay? So if that affects you, please note the new location. And Wiley Plus, the demonstration will be done by the Wiley Plus student representative, who also happens to be a TA in this class. So that demonstration on how to navigate that will be done by your TA, Brian, for a few minutes at the beginning of lecture on Friday. It is pretty straightforward, but we thought that we start by just having everybody be on the same page and doing the demo in class. And obviously, if you have any issues, let us know. And if there's any technical hiccups, all of that, let's resolve them now before before the week that your homework is due. Okay, so take a look at it and let us know if there are any glitches. Okay, so here is Carmen. It should look something like this. Your landing page is going to be the modules page, okay? So this outlines in a linear fashion and aggregates all the documents that are posted in one place. You should not have to be searching for something. If you are, you're probably not in the right place, or it wasn't posted correctly, right? It takes 2 to tango, so it could be you or it could be me. So consult your colleague. If your colleague's also having an issue, it could be us. It could be a permissions issue. It could not, or if there's a delay in the posting for whatever reason, we'll let you know. I do not send out emails every time something is posted. And really, the only thing that gets posted most frequently is the lecture recordings and then, of course, the lecture slides, right? You don't need a ping from me every single time something goes up, okay? So please just check it regularly and work at your own pace. If you watched the lecture recording, you may have noticed that it is not on MediaSite, but it is on YouTube. I do believe in the democratization of education, and so it is there not only for you, but for the World Wide Web to digest, and we build a bigger materials community by sharing our knowledge, right? And so it is on there. So if you're already on YouTube, you can subscribe to it, and then you get a ding every time I upload, and then it can be a passive reminder, and it won't spam your inbox, okay? So that's that. All right, so you could see the intro lecture slides have already been posted, but you already knew that because it was up there already. I reposted it in the intro module as well because there's some overlap to that, so it's not just the syllabus, right? If you've been here day one, which the majority of you have, you should have already seen that. The lecture recordings are going to be by date, so if you miss a lecture, you can view the recording there, and they'll be in chronological order. The homework you should see here is already open, so your TA will go over this. And then any of the readings will be here. Your assignments, your e-textbook, and announcements will all be there. And of course, discussions is also there. So pretty straightforward, just an integration of Wiley Plus into Carmen. So that might be a little bit different if you haven't used Wiley Plus for other classes before. My guess is if you've taken Gen Chem or something like that, you may have had different programs like the mastering series. This is obviously very different from that. So just familiarize yourself, okay? Okay, any other questions about some housekeeping things before I start? Okay, great. You've also may have noticed that there's a bajillion devices on this counter. There's a reason to this madness. I've noticed that the resolution that's posted as recorded by the media site that's integrated into this podium is a little bit lower than optimal. So a ticket has been submitted, but in the meantime, I'm trying a hack with Carmen Zoom to get better resolution of the screen capture. That involves my iPad being able to mirror its screen onto here to project onto here. There have been a number of issues, and so a ticket has also been submitted to resolve this. So for today, we'll still record via media site, because there's every technique I've tried, there's been one glitch where one device does not work with the other. So maybe if you're very talented, you can volunteer some solutions. The TAs are also working on it to help me. But for now, the next video, the resolution might be a little bit lower than optimal. But we will get there, right? The devices will not get the better of us. Okay, but we'll go with the podium. Oh, we should start from the beginning. All right, so we'll have some top hat questions for practice today as well. So you don't have to get your devices out until we come to that. And of course, these lecture slides have already been uploaded yesterday. Okay. All right. So now we dive straight into chapter 2, which covers atomic structure and interatomic bonding. If you've already done some of the reading, you've noticed that some of the terms and concepts might be very familiar, and it should be. I should reiterate, this should be a review. A lot of the concepts are covered in general chemistry. I know there's some quantum mechanics that are in there, but most of it, if not all, really should have been covered by Gen Chem, in your Gen Chem and in your general physics course. So the entirety of today and Friday should really be review. I don't want to sound like a broken record, so I won't say, well, you should know this, or, oh, remember from Gen Chem back in the day when we were talking about orbitals? That is the stipulation, okay? So, so if it's not familiar to you, or it's been 3 years since you've taken it, maybe 2 years, maybe you took an AP Chem course, so it's been a while, look through it, familiarize yourself again, okay? But it should be review, and if it's not, come to recitation with all your questions, okay? Or office hours, or both, okay? All right. So why do we care about bonding and all that? Because, as I said during the first lecture, understanding how atoms behave, how atoms pack, which is chapter 3, and of course how each atom bonds with each other will dictate everything that you see, all the properties that you see at the end of the day. So I can tell you if a material will behave as a high-performing intercalation material if you just tell me the structure of the material. Or if you give me the compound stoichiometry or composition, I will be able to tell you that based on the general theory and principles of chemistry and physics, right? So before you even say, oh, well, should we do all this testing and, yada, yada, and do all of this service and fatigue and all of that, I could tell you there are certain elements, and you, at the end of the day, should also be able to say, no, this element or this material would not be even a good start based on these theories. Obviously, material science and engineering is forever evolving, right? So what we actually knew about material science, particularly in nano, has revolutionized the world, but it's evolving, and we didn't have the formalism of nanotechnology, until really quantum mechanics. So, and really, the latency was all the way to maybe the 50s, 60s with the transistor, right? So anyway, that's, one could go into a whole class on that. But at a minimum, you should be able to predict melting temperature, thermal expansion, elastic stiffness, electrical and optical properties, just based on your understanding of the bonding and packing of atoms. And so, of course, we're going to be talking about the formalism by which we use to describe atoms and how they're bonded and what systems they belong to, what type of material system they belong to. So if you read, let's start the top hat to get the blood. Whoop. All right. So if you recall, my goodness, how many clicks does it take? All right, so which bonds are primary bonds that are directionally dependent? Well, what does that mean to be a primary bond, and what does it mean to be directionally dependent? This affects strength of a material. It is the reason why graphite can slip past each other. The carbon atoms and graphite can slip past each other in one direction and not the other directions. It is also the reason why the allotrope diamond is one of the hardest materials you can find out there, but it's all made of carbon. And this is why. So register your answers. We're almost there. A few more folks, and then we'll close it. All right, the last 4. We may have to go on without you in 5. 2 more folks. Oh, okay. 3 more folks. All right. Oh, fabulous. Okay, great. So let's see. Let's see what you. Oh, fabulous. You remember a lot, or you read, or both. So yay for us. Okay, it is exactly what you think. Well, one, van der Waals, you can get rid of that, right? Because it's a secondary bond. So we're going to talk about it. So now you're down to 1 out of 3, and of course, covalent bonds are directional, right? That means they have when you bond 2 atoms together, their orbitals have to be aligned along a certain direction for it to bond, whereas ionic bonds are not. So that rules it out. And some covalent bonds are in metal, so they have some metallicity in them. So it looks like the toss-up, well, there isn't really a toss-up, but the second choice was ionic. So you may have thought, well, ionic, the atoms or the ions have to be in a certain direction, right? Because they're electrostatically attracted to each other or repelled if it's the same charge, right? So that's probably what you were thinking when you chose ionic bonding as directional, but that's not the case. So, we'll dive into detail as to what does it mean to be directionally dependent and what is a primary bond. So the majority of you got it. Fabulous. Start, everybody. Okay. Okay. So for the record, oh dear. Okay. Okay. You didn't really need to know that, but that for just redundancy. Okay, so at the end of the day, which is really the end of chapter 2, what should you be getting out of this, right? You should know the atomic models that are cited. So we'll talk about the Bohr model. We'll talk about the wave mechanical model, right? So if you've taken quantum mechanics, you know that electrons can behave as waves or particles. And then describe how we use this formalism as it relates to electron energies. This will be particularly useful much later in the semester as well when we talk about electronic properties and electronic states. Okay? And of course, then talk about when you bring two atoms together, whether they're neutrally charged or ionically charged, you know, what determines the bond length, right? So you should be able to talk about that in some reasonable, coherent fashion. And then, of course, describe the ionic, covalent, metallic, hydrogen, van der Waals bonds, and the properties that arise from having these types of bonds within the system. Okay, so let's talk about the two models. You can have discrete energy levels like the one in the left. So these are figures from your textbook. You could just have these electrons occupy different orbitals of discrete energies. So here you can have electrons here, here, and they can occupy this level of energy or, you know, this orbital. And you can pretty see that there's symmetry here, and there's no shape to this sort of model. Now, the quantum mechanical wave model says that they're actually shaped, their energy levels are quantized, and also there's a distribution. So you could see here that there's a distribution. You see this haze or these dots here. There's a distribution as to where you can find this electron, right? And this is given to us by the Heisenberg uncertainty principle, where if you know the momentum exactly, you don't know where it is spatially, and vice versa, right? So, and their dot product has to be greater than h bar over 2. Okay. So there's a probability of finding an electron somewhere. And so when we say things like, oh, the electron is in the 1s orbital, we really mean there's a 95% chance of finding the electron in that orbital. That's the quantum mechanical model, right? So because there's always some uncertainty there. Okay, but we treat it when we talk like it's with such certainty, right? Where it's 1s2, 2s2, 2p2. We say it with such certainty, but there's always a very small percentage that it might not be there, right, given any quantum fluctuations. And this is becoming obviously more and more important since the theory was developed in the 1920s by Schrödinger and Einstein and all these, Heisenberg and Bohr. It's becoming much more important these days, right, with a lot of research that's going into quantum computing and quantum mechanics and quantum entanglement, right, where these particles now can occupy multiple states of energy that weren't possible before. So how do we untangle this? And of course, that affects cybersecurity and all of that. So, very important model. Okay. Oh, there's a little bit of a lag for some reason. But okay, so formalism. You got your atom, fabulous. Then you have your subatomic particles, your electrons, your protons, your neutrons. You can see the masses of electrons are significantly less than that of protons and neutrons, which are each 1.67 times 10 to the minus 27 kilograms. So you should be able to have a feel as to the scale of which you're dealing with, right? This should be all review, but you know, we'll get to feeling of units and when things don't make physical sense. All right, when we talk about atomic number, we're really talking about the number of protons in the nucleus and the number, which should be the same number of electrons, right? And this is for a neutral case. If you're talking about a cation or an anion, you're talking about charged species. So that might not be the case anymore. And then the atomic mass unit, or AMU. It's defined as some fraction of the weight. And the weight is really a weighted average of all the masses in terms of different isotopes. So what is an isotope? Well, if you have read about carbon dating, you probably have heard of C14 versus C12. Okay, C12 is the naturally occurring carbon, but there are different number of neutrons between C12 and C14, right? So when I say 12, I'm referring to the atomic number, which is the number of protons in the nucleus, but it could have different neutrons, so C12 versus C14. So I put conversion here because these are the units that we often work with. If you've seen the periodic table, which I know you have because you've taken Gen Chem, you'll see that it looks something like this. Okay, so you have your atomic number here. This is already defined in your book, figure 2.8. But you can see that you have your atomic number and your atomic weight. So that's a weighted average of all the isotopes in the abundance. So we often refer to this atomic weight as, for here, the example of copper is 63.55 grams per mole. But you can also refer to it as, 55 AMU per atom. So that all of that should be interchangeable. So the example that I have, which is also your homework question number 1 in part, is really just to get you familiar again with these types of units. So if you're asked, how many grams are there in 1 AMU of a material? Any material, you can manipulate it once you look at the periodic table, but of any material, well, how do you get there? So the question asks for, some X grams of in 1 AMU. Okay, and we know that there are in 1 mole, how many atoms are in 1 mole? Avogadro's number is what I heard from the gentleman in the cap. What is Avogadro's number? Okay, you're going to have to shout it out a little bit more. Fabulous. Very participatory. Thank you. Right, so Avogadro's number. And we know that there's 1 gram per mole and 1 AMU per atom. All right. So this all cancels out, and if we plug into Wolfram alpha, we get something like, or your calculator, so now we have another conversion that we can use, relating 1 unit, gram, to atomic mass unit. Okay. So really just familiarizing yourself with the with dimensional analysis and the different units that we often use. So that's it. So the second part in your homework asks you to relate a pound, I think a pound mole or a gram pound, something like that. So basically, you have to convert between pounds and grams, right? So you might have to Google that or look in your book, right, in the appendix. But that's about it. Yeah. That is another relationship that we use to convert. So in the so that unit 63.55, that is grams per mole. Oh, no, sorry. Well, if it's copper, it would be 63.55 grams per mole. The assumption was going from grams to AMU, and we know that 1 AMU per atom is 1 grams per mole. So how do we relate that back to, or grams back to that? That is the standard unit. Yeah, and that is in your textbook. I think it's, well, section 2.2. Sorry, 2.1, 2.2. Yeah. Okay. Is the AMU constant for all materials? It is, well, so in terms of fractionally, Yes. Is it one AMU per atom? Yeah. That's the same. Yeah. But here, right, for all materials, if you're talking about copper, it's 63.55. If you're talking about nickel, it's 58.69. Yes. So why do we keep going back and forth with this? Because sometimes we're talking about an atom. Sometimes we're just talking about removing one atom from the system, like ionization. Well, that's electron, sorry. Or dopant, sorry. Let's say you have an impurity. You're talking about a low concentration of atoms, and you say, okay, well, what happens if I remove one atom or a small fraction of that? Then it makes more sense to be per atom versus per mole of something, per Avogadro number of something. You don't want to be dealing with 10 to the 23rd, atoms per mole. So what you see here is typically when people refer to these molar masses, they say, it's 63.55 for grams per mole for copper. But if you're talking about one copper atom, the energetics, the number that you deal with, sometimes makes more sense to just deal with atoms. And that's why we're doing this exercise to go from moles to atoms, AMU versus grams. Okay? So that's the standard definition. Okay, this will become more obvious when we talk about, let's say, diffusion. When you're talking about atom moving from one lattice site to another lattice site, that energetics is often compared to each other as EV per atom. Right? Most people don't use that. That would be the convention, and so it's good to work with these types of units and become familiar with them. Okay, so. Now that we've done just a little bit of review, let's go, in terms of dimensional analysis, let's jump to electron configurations, okay, and talk about the valence electrons. These are the electrons that you care about unless you're trying to, of course, excite an electron from a core orbital. These are the electrons that are in the outer shells. Okay, and what do I mean by outer shells? We'll get to the quantum numbers of that. So, of course, as you remember VSEPR or the octet rule, you remember that the filled shells are more stable, right? They don't need to get another electron, or they don't need to donate an electron to become stable. So, like all your noble gases are stable because they have filled shells. And when we talk about shells, we talk about the example of, let's say, 2p2. That is the outer shell. So the electrons in that orbital would be the valence electrons. So in carbon, there are 6. The atomic number is 6, so there should be 6 electrons in the neutral state. So then we start filling 1s2, 2s2, 2p6. Okay? So when we talk about 1s2, 2s2, 2p6, 3d10, we're talking about the quantum numbers. We're talking about the 1, 2, 3, 4, right? That's n, the principal quantum number. That tells you how far the electrons are away, the size of the orbitals, how far the electrons are away from the nucleus, right? And then we talk about the azimuthal number, L, and that tells you the shape. So 1s, S being spherical, so that's the example you see here. And then the p orbitals, you see they have a different type of shape. So px, py, pz are along different axes, and they look more like these lobes. Conventional would be dumbbells, if you want to call them that. But they have a different shape to them. And then you can have a subset of that. So here's the example of the d orbital. So they can get more complex. Now, why does this matter to you? It matters because depending on how atoms are, these orbitals are arranged, you can definitely dictate the bonding and the strength along that direction just by choosing certain elements to make up certain materials and certain compositions when designing materials. And so this is more relevant for, let's say, transition metals when there are 3D orbitals in them. So that starts with scandium, titanium, vanadium, and so on and so forth in the first row, and then the 4D transition metals, and so on and so forth. So the table in your book works out the schedule of which, how many orbitals there are and the number of electrons there are in the system. So you could see that 1s has 2 electrons. So the S's have 2 electrons, the P's have 6, the D's have 10s, and the F's have 14. Okay, and so we can design all of we can note all the electron configurations through this system. Okay. And here are the energetics. So if you remember, there was a scheme. You might have learned different schemes in your Gen Chem class, but the review is also in your book in terms of the energy. So here's the principal quantum number, so 1s, and then it rises in energy this way. So you could see here that 3s, 3p, and then 4s, 3d, and then it jumps to 4p. Okay. So there's a little bit of a quirk in this system. It's not always as linear as you may think or recall. Okay. Right. So the unreacted species, we just talked about the noble gases, and here are the electronic configurations for helium, neon, argon, krypton. So you could see that all their orbitals, 2p6, s2, 3p6, 4p6, you can have 6 electrons in the p orbitals, and they all have that. So they're pretty unreactive, right? And of course, they're all gaseous species, but you could predict that based on the knowledge that they're filled orbitals and that they're not going to react with other elements, and they have low melting points. Okay. Other systems, here's just a subset. You could just work out to your heart's content every single element, but you should be able to build it up. So the atomic number for hydrogen is 1, so the number of electrons is 1. So you start building 1s1, helium's 2, so you fill the orbital to 1s2 because you can have 2 electrons in the s orbital, and then this is just now iterative and pretty tedious for lithium and beyond. I should note that even though there are 3 electrons in lithium, it is one of the most studied metals there are out there for obvious reasons. Does anybody have a guess why? It's probably in every single one of your pockets. Yeah, your batteries. And there are huge geopolitical issues and mining with that goes with lithium, and we'll talk about that when we talk about the economic issues with material science. But okay, so what is the electron configuration of lead? Does anybody want to work through this with me? Lead is here, by the way, in case you're looking for it. I chose specifically a high atomic number so that we can all go through this together. Anybody want to take a shot at it? We can all chant together as a class if you don't want to do it by yourself. So let's start. 1s2. Oh, well, actually, we're here now. Next. 2s2. Next. 2p6. Next. 3s2. Next. Next. And then. And then. And then. And then. Oh, and then we hit the lanthanides. Five, four. Okay, I hear some commitment to 4. And then All right, so hopefully that was as fun for you as it was for the rest of the class. Okay, so that's how you do it. It's pretty straightforward. Is it a filled shell? No. Great. So of course, the reverse could be asked of you, which element has the following electron configuration? Zinc. How do we get there? 3d10. So sometimes you can just look at the valence shell, and that will just tell you, okay? Speaking of the valence shell, you could also see this notation. So if you have krypton here, and you go 5s1, 2, you could end up with strontium, okay? What if it's strontium 1+? Let's say you could even do that. It would be not typical, but let's say you could get strontium 1+. How would you rewrite this? I'm sorry? 1+? Oh, how would you rewrite this configuration if it's strontium 1+? So you remove one electron from strontium now. S1, yep. It's redundant to write the 1. Okay. Okay. Right. So valence structures. This segues us into ions, right? So you can start stripping electrons or add electrons to the neutral state. So the columns on the left here, as you recall, the alkali metals, they're willing to give up one electron pretty easily. So lithium 1+, that is the ion that we were referring to that intercalates into and out of the cathode materials in your batteries. So you typically find lithium metal, so lithium 0, or lithium 1+. Those are the common states that you'll find it in. If your alkali earth here, oops, sorry, that was a little too wide. These atoms tend to give up 2 electrons, and then this column tends to give up 3 electrons. The transition metals, you can have multiple valences, so titanium could be most often 4+, but could also occur in the 3+ state. Vanadium is stable in the 5, 4, 3, and possibly +2 states, and that's what makes it interesting as a material in the oxide form, but also in the sulfide form, and then so on and so forth. So the materials that maybe you've worked with, if you worked in industry, from the person that used to sit over there in lecture 1, if you worked with metals, you would be expecting, let's say, a neutral state like iron metal or nickel metal. But often there are oxidized states at the surface, right? So if you worked with aluminum, you have definitely worked with aluminum oxide, Al2O3, because there's always a passivating layer that prevents further oxidation or further rusting into the material. So even if you worked with metals before, it could be, 3D transition metals like these, you probably would have worked with also oxides, and you may or may not have known it, or you may have known it and tried to prevent it. That could have been your research. And then the elements that are on the right side, this column tends to accept 2 electrons, right? So if you remember, oxygen tends to be 2-. It accepts those 2 electrons because it wants to have the filled shell. And then the halogens or halides will accept 1. So often you have F-, Cl-, Br-, right? It's accepting that 1 charge, and then you have your inert gases that we just talked about. Okay. We also use this empirical based system called electronegativity to talk about how easy it is to acquire or lose electrons. So here on this side of the periodic table, there tends to be smaller electronegativities, and on the right side, there tends to be larger electronegativity. And so here we tend to talk about them as electropositive and more electronegative. And then there's also, a guiding rule of thumb that if the larger the differences are for the electronegativities, you tend to have more ionic bonds. Now, where the cutoff for that is a little bit hazy, but it tends to be, if the difference is 2 or more, tends to be ionic type of bond. but you can get exact percentages of ionic character through a simple relationship that we'll talk about, and it's also in your book. Okay, ionization process, right? We talked about +1, +2, -1, -2, right? You're removing electrons, and so you could think about here or adding electrons. So here, the classic system of periclase, magnesium oxide. Magnesium is in its neutral state, has this electronic configuration with the valence electrons of 3s2. And so if it's 2+, it gives up those 2 electrons, and it becomes 2p6 as a valence orbital. And oxygen likewise accepts the 2 electrons and now has a filled shell of 2p6, right? So when we talk about these compositions, all of this math has already been done, right, to satisfy these general chemistry principles. Okay, so let's talk about bonding within the 3 different classes of material. Okay, we'll talk about metals, ceramics, and polymers. So how does the bonding relate to these properties that you may have heard of or that we'll talk about a lot, right? So metals tend to have ductile, the properties, they're conductive, they tend to be a little bit denser, they have high strength, they're reflective, and they have moderate melting temperatures. All of this can be related to the bonding types that are in the metal. So when we talk about iron, iron, or nickel, nickel, copper, copper, zinc, zinc, things like that, that is a type of metallic bonding. Ceramics, right, the properties that you often observe are that they can be brittle. They're insulating, they're opaque, but they can also be transparent if they're single crystal. So a lot of the sodium lights that you see for street lamps, right, those are high temperature lamps, but the coating around them, you can see them, it's because it's single crystal coating, so it's transparent. So it's not always opaque. And that they're high melting temperature. So what does ionic bonding have anything to do with the fact that these ceramics have high melting temperatures, right? So we'll talk about that. It has everything to do with the bond energy in the system. And then polymers, right? They run the gamut, right? If you have single crystalline, they could be brittle, they could be ductile. They have low melting temperatures. And why is it that they have low melting temperatures relative to the other 2 classes of materials? It has everything to do with van der Waals bonding in the system. And those type of bonding is called secondary bonding. Okay, so bonding types. We'll go into the delocalization of electrons, or the electron sea, the electron cloud that is around all of the metal atoms in the system. And in the end, what it looks like is you have these somewhat positively charged metal cores with a sea of negatively charged electrons. Okay, so that's what it looks like. And so here's just an example of something that's FCC, face-centered cubic, and that's a term we'll go into depth in chapter 3. But if you have metals that, they could pack like this, let's just say. What really happens is at any instantaneous moment, the electron sea or the electron cloud tends to look like this, where you have this delocalization of all the electrons in the purple here, and the cores of these metals can be slightly positively charged. So then you think, well, shouldn't they repel each other if they're all charged the same way? They're slightly charged that. And the electrostatics is shielded so that these electrons shield the repulsion between each of these pairs. Okay? So that's the metallic bonding structure and type. And you could see that a lot of the elements in the periodic table are metallic. So that's in this light blue color. So you could see here, like the vast majority of them are metal. So this is pretty important bonding to understand in terms of predicting materials properties. Okay. Then you have covalent. You've seen this in glasses. You've seen this in polymers, where here you have, these are carbon-carbon. So you can think about carbon-carbon chain, let's say, or in methane. So here's the bonding. And so there are different types of bonding, but the valence electrons are shared. So this is what I mean by directional. You cannot share an electron from your orbital with another orbital unless they overlap somehow, right? So it has to be in the same direction as the other orbital. Whereas the ionic bonding, it can be statistically distributed in any direction. It's more, well, the orbitals still overlap, but the electrons are transferred and they're not shared. Okay, so you need to be in the same direction as the orbital of the next element that you're sharing your electrons with. And typically where you find covalent bonding is within elements that have similar electronegativities. As I've said, the cutoff between what is covalent, what is ionic, is about a difference of 2 in the electronegativity, but that is sort of an agreed upon cutoff. There's always some sliding scale, some percentage of ionic character, okay? And you can see, where do you find covalent bonding? Well, everywhere, basically, other than metallic bonding. And even though I said this is not a primary class of material, it is a very important class that we'll talk about in electronic properties. Okay, more covalent bonding. So here's just some examples to go more in depth. You have covalent bonding in hydrogen, right? So if you have the 2 elements that are the same, the electronegativity difference is going to be 0. And that goes the same for, you know, the fluorine, chlorine, elements that are close to each other, gallium arsenide, let's say, silicon carbide, all the diamonds, the allotropes of carbon, graphite as well. Okay. And of course, within the molecule, H2O. But there's also hydrogen bonding within H2O. So there could be mixtures of bonding. And here's a good example of directionality, right? And this is the exact reason why diamond is hard and why graphite is softer in one, or can glide past, the carbon atoms in graphite can glide past each other in graphite. So you can see here hybridization. So when we talked about 1s2, 2s2, 2p6, 2p2 in carbon, right, we talked about them as if these electrons just occupy these different orbitals. But of course, the orbitals can also combine and hybridize into these other orbitals. So if 2s and 2p hybridize, they could form 4sp3 or 3sp2. And so the directionality is that here, between the orbitals, this is 109.5 degrees, and the angle between the sp2 orbitals are 120 degrees, right? So then you think, okay, well, if that's sp, let's say x and spy that have hybridized, what happens to the pz orbital, the one sticking out? Let's say, if this is z. Well, it's not hybridized. So then it experiences van der Waals interactions with the next layer, which allows carbon to do, graphite to do this, which is the only reason why pencils work the way they do, right? Yeah? Can you explain hybridization a little bit, sort of like math and orbitals and why? Yes. So it has everything to do with lower energetics, right? When you hybridize these unfilled orbitals, it can lower the energy of the 2 systems a little bit, and that allows you to bond in a certain way. So when diamond, you have these sp3 hybridization, they lock into this structure that makes it stronger than, say, graphite that has an unhybridized orbital, which is your pz orbital. So it's always about energetics. It's always about the thermodynamics of the system. Can you go to a lower energy system? For carbon, in this particular case, if you hybridize s, 2s, and 2p, it will give you slightly lower energy and thus result in this sp3 hybridized system versus, let's say, some sp2, which occurs in graphite. Now, how does it get there, right? Well, it's all based on the conditions. Obviously, diamond grows in different conditions than, say, that of where you would find graphite, right? So under a lot of pressure, a lot of high temperature. So, this type of bonding might not exist under certain conditions than, let's say, under ambient conditions like this. Okay. Well, once diamond forms, obviously, it's stable up until a finite period of time, and then it will disintegrate. Okay. Okay, ceramics, ionic bonding. Right, so electrons are now transferred, they are not shared. Right, so the example, magnesium oxide, we'll continue that with additional examples like sodium chloride. One electron is transferred from sodium over to that of chlorine, now becomes chloride. Same thing, calcium, difluoride, 2 electrons, cesium chloride, 1 electron gets transferred from cesium over to chlorine, giving you chloride. Okay, so pretty standard. And now secondary type bonding. The classic example is that of H2O. So in the solid form, otherwise known as ice, right, you have this open type structure because the hydrogen bonding between let's say, the slightly positive charge between, the slightly positive charge of hydrogen with that of the next oxygen, as seen here, right, forces it to be this open structure, right? And a more open structure is a less dense structure. And so what happens when something is less dense than something else? It rises to the top, right? So in the liquid form, H2O is more dense. In the solid form, it's a more open structure, so it rises to the top, which is why you have ice on top and water on the bottom, and all the fishies thank you for that. Okay, so where you find these types of bonding, well, there's quite a number of them. There's fluctuating induced dipole. So what does that mean? So it means that whenever we have these electron clouds, right, even in H2, right, where you think, okay, it's the same element, it's 1s1, here's some distribution of electrons, but in any instantaneous moment, there's a fluctuation, and that fluctuation causes one side to maybe be a little bit more positive than the other side, and that then allows this type of attraction to occur, and thus you can keep it together, right? So that's fluctuating induced dipole. Then you can also have polar molecules, right? So the example is HCl, and then you can also have the permanent dipole, where these two, right? So positive and negative, can attract each other, and then you have hydrogen bonding, which would be stronger. Okay. And of course, hydrogen bonding occurs in compounds with hydrogen. Okay, let me, with the amount of time, let me not continue on to ionic character just yet, because there's an example problem that I want to dive into in terms of mixing bonding. So let's stop here and continue chapter 2 Friday, and we'll end with chapter 2 then as well.